Welcome you in the lecture series of random processes, detection and estimation. It is 22nd lecture of this series. In the previous lecture, we have discussed Bayesian linear model. In this lecture, we will discuss Gaussian random signal with unknown parameters. And the outline of this lecture are General Gaussian detection, Gaussian random signal with unknown parameters, where we will discuss the incomplete unknown signal covariance and with unknown signal power. And after this, we will discuss weak random signal detection. In the objective of this lecture, you will be able to explain where the general Gaussian detection is used, and you will also be able to explain how can you detect a random signal which has unknown parameters. Now we start with the general Gaussian detection. We have already discussed the detection of the deterministic signal in white Gaussian noise. In previous two lectures, we have discussed the detection of a random signal in white Gaussian noise. In general case, the signal is allowed to have both deterministic and random components, and the signal is modeled as a random process with the deterministic part corresponds to a non-zero mean, and the random parts corresponds to the a zero mean random process with a given signal covariance matrix. These assumptions leads to general Gaussian detection problem in which the signal can be discriminated from the noise based on its mean and covariance. Mathematically, the general Gaussian detection problem can be described by the two hypotheses. With hypothesis H0, x is equal to omega, means there is no signal, only noise is present with hypothesis H0, and with the H1, x is equal to s plus omega, where omega is the random process with zero mean and covariance matrix C omega, and Sn is the random process, normal process with the mean mu s and covariance matrix Cs, where here s and omega are independent. The NP detector decides H1 or H0 if the likelihood function means the PDF under hypothesis H1 divided by PDF under hypothesis H0 will be greater than less than some threshold value gamma. So the PDF under hypothesis H1, it will be 1 by 2 pi to the power n by 2 into 1 by 2 under root determinant of the matrix Cs plus C omega into e to the power minus 1 by 2 transpose of the matrix X minus mu s into inverse of the matrix Cs plus C omega into X minus mu s, and the PDF under hypothesis H0, it will be 1 by 2 pi to the power n by 2 into 1 by under root determinant C omega into e to the power minus 1 by 2 x transpose inverse of C omega into x, and it will be greater than less than threshold value gamma. Taking the logarithmic, retaining only the data dependent terms, and scaling produces the test statistic Tx, it will be x transpose inverse of the matrix C omega into x minus transpose of the matrix X minus mu s and inverse of the matrix Cs plus C omega into X minus mu s. I can also write it as X transpose inverse of C omega into X minus X transpose inverse of the matrix Cs plus C omega plus 2 X transpose inverse of the matrix Cs plus C omega into mu s minus mu s transpose inverse of the matrix Cs plus C omega into mu s. And from the matrix inversion lemma, I can write it as inverse of the matrix C omega minus inverse of the matrix Cs plus C omega. It will be equal to inverse of the matrix C omega into Cs and inverse of the matrix Cs plus C omega. By ignoring the non-data dependent term and scaling, we will get the test statistic T dash x transpose Cs plus C omega inverse into mu s plus 1 by 2 x transpose inverse of the matrix C omega Cs and inverse of the matrix Cs plus C omega into x. This test statistic consists of a quadratic form as well as the linear form in x. Now we can have two cases. Case first, when Cs is equal to 0 or deterministic signal with S is equal to mu S with mean value mu S, then the test statistic T dash x, it will be x transpose inverse of the matrix C omega mu S, which is our pre-Whitener or meshed filter. Case second, when mu S mean value of the signal is 0 or random signal with normal distribution with mean 0 and covariance matrix Cs, then the test statistic T dash x, it will be equal to 1 by 2 x transpose inverse of the matrix C omega Cs and inverse of the matrix Cs plus C omega into x, and I can write it as 1 by 2 x transpose inverse of the matrix C omega and x s cap is this part, where s cap is the Cs inverse of the matrix Cs plus C omega x. This is the minimum mean square error estimator of S, and this is pre-Whitener followed by the estimator correlator. Now let us take one example. There are two hypotheses. H naught corresponds to xn is equal to omega n, means under hypothesis H naught there is only noise, and under hypothesis H1 xn is equal to Sn plus omega n, where n is from 0 to n minus 1, and omega n is the white Gaussian noise, and Sn is the normal distribution with mean a and variance sigma s square. Sn is independent from omega n. Sn are independent identically distributed. So Sn can be considered as the sum of the deterministic DC level due to A and white Gaussian process with variance sigma s square. Find the test statistic. So here let C omega is equal to sigma square into I, covariance matrix of the noise. Mu s is equal to A1. Here 1 is the matrix of all 1, and Cs is equal to sigma square into I. Now with NP detector, the test statistic, it will be T dash x is equal to x transpose and inverse of the matrix sigma s square I plus sigma square I into A into unit matrix 1, and the matrix which is having all ones, plus 1 by 2 inverse of x into 1 by sigma square identity matrix sigma s square identity matrix and inverse of the matrix sigma s square I plus sigma square I into x. So I can also write it as NA by sigma s square plus sigma square into x bar plus 1 by 2 sigma s square by sigma square divided by sigma s square plus sigma square summation n0 to n minus 1 x square n, which attempts to discriminate on the basis of mean xn and average detector, and energy detector which attempts to discriminate on the basis of the variance 1 by n summation n0 to n minus 1 x square n. Now we will discuss the detection of Gaussian random signal with unknown parameters in white Gaussian noise, but it was it was restricted to the white noise. The color noise problem is a simple extension of this. So in this random signal with unknown parameter, first we will consider incomplete known signal covariance. Let two hypotheses are. Hypothesis H0 corresponds to Xn is equal to omega n, means under hypothesis H0 there is only noise, and under hypothesis H1 Xn observed samples are is equal to Xn plus omega n, where small n is equal to from 0 to n minus 1, and Sn is Gaussian random process with zero mean and covariance matrix Cs, and omega n is the white Gaussian noise with variance sigma square. The signal covariance matrix depends on some parameters which are unknown. For example, we might not know the power of the signal. If Sn is wide sense stationary process, then autocorrelation function RSS0, it will be the mean. It will be the expected value of S square and mean square value of the signal from the property of autocorrelation function. RSS0 will be equal to expected value of S square n. And now for n is equal to 2, the covariance matrix will be Cs is equal to with the elements RSS0, RSS1, RSS1 and RSS0. So I can write it as RSS0 1 minus rho 1. So here rho is the correlation coefficient and it is equal to RSS1 divided by RSS0, and assume it is known. So the PDF under hypothesis H1, it will be 1 by 2 pi to the power n by 2 under root determinant of the matrix Cs plus omega square I into e to the power minus 1 by 2 x transpose inverse of the matrix Cs plus sigma square I into x. To implement a GLRT, we must maximize this likelihood function over RSS0 to find the maximum likelihood estimator. So it may be difficult to evaluate the determinant and the inverse of the covariance matrix. Now let us take two cases. Case first, the unknown signal power, and the case second, unknown signal power with white signal. So in the first case, let us take one example. Consider the previous example, and if a random Gaussian signal Sn is embedded in the white Gaussian noise with variance sigma square, then it has the signal covariance matrix as Cs is equal to RSS0, RSS1, RSS1, RSS0. It will be RSS0 1 rho 1, or it will be P0 1 rho 1, and I can write it as P0, and this is C, covariance matrix C, where Cs is equal to P0 C. From this you can say that Ps is equal to P0 C, and P0 here is RSS0, where P0 is unknown and C is known here. Find the equation to minimize that gives MLE for P0 or RSS0, and we know that the signal covariance matrix, and we know the signal covariance matrix. So the PDF under hypothesis H1 is Px P0 H1. It will be 1 by 2 pi to the power n by 2 determinant 1 by 2 matrix P0 C plus sigma square I into e to the power minus 1 by 2 x transpose P0 C plus sigma square I inverse into x. To implement GLRT, we require to determine the MLE of P0, and here the determinant under root determinant of the matrix P0 C plus sigma square I, it will be determinant of P0 V lambda V inverse plus sigma square I, where V is V1, V2, V3, Vn is the eigenvector, and lambda is equal to diagonal lambda 1, lambda 2, lambda n, which corresponds to the eigenvalue of the C. I can write V transpose equal to V inverse. V is an orthogonal matrix, so C will be equal to V lambda V inverse, and the determinant of determinant 1 by 2 P naught C plus sigma square I, it will be equal to determinant V P naught lambda plus sigma square I V inverse, and I can write it as determinant P naught lambda plus sigma square I, and it will be equal to pi I1 to n P naught lambda I plus sigma square. So P naught C plus sigma square I, it is P naught inverse of the matrix P naught V lambda V inverse plus sigma square I, and it will be equal to V inverse of the matrix V into P naught lambda plus sigma square I V inverse. We have the PDF under hypothesis H1. It is 1 by 2 pi to the power n by 2 under root determinant of the matrix P naught C plus sigma square I into expected into is to the power minus 1 by 2 x transpose and inverse of the matrix P naught C plus sigma square I into x. Now taking a natural log, we will get log E Px P naught H1, it will be equal to minus 1 by 2 log E 2 pi minus 1 by 2 summation I1 to n log E P naught lambda I plus sigma square minus 1 by 2 x transpose V inverse of the matrix P naught lambda plus sigma square I V transpose x, and it can be written as minus 1 by 2 log E2 pi minus 1 by 2 summation I1 to n log E P naught lambda I plus sigma square minus 1 by 2 summation I1 to n V I transpose x whole square divided by P naught lambda I plus sigma square. So P log E P x P naught H1 log of the PDF under hypothesis H1, it is minus 1 by 2 log E 2 pi minus 1 by 2 I1 summation I1 to n log E P naught lambda I plus sigma square minus 1 by 2 summation I1 to n V I transpose x square divided by P naught lambda I plus x square. And here V transpose x is the V1 transpose x, V2 transpose x up to Vn transpose x. This is the matrix form, column matrix, and here to find the MLE of P naught, we must minimize this term, this part. So we should minimize J P naught, this is the function of P naught, summation I1 to n log E P naught lambda I plus sigma square plus V I transpose x whole square upon P naught lambda I plus sigma square. It is non-linear equation in P naught, the general solution of which is unknown. For some special case, we can find out P naught, like in the next example, when the unknown signal is white signal, and if all lambda i's are equal, that is lambda is equal to lambda, so then Jp naught, it will be n log E P naught lambda plus sigma square plus 1 by P naught lambda sigma square summation n1 to n summation I1 to n Vi transpose x whole square, and it will be equal to n log e p naught lambda plus sigma square plus 1 by p naught lambda plus sigma square x transpose x, and this case corresponds to C is equal to V lambda V inverse, or it is equal to lambda I, or the random signal in white. And after taking differentiation, you will get lambda n lambda divided by p naught lambda plus sigma square minus lambda x transpose x divided by p naught lambda plus sigma square, and whole square of this term p naught lambda plus sigma square is equal to 0. And then you will get the estimated value of the power p naught cap. It will be 1 by n summation n 0 to n minus 1 x square n minus sigma square by lambda. Here p naught greater than 0. If p naught less than equal to 0, then MLE will be the 0. So the MLE is p naught cap is equal to maximization of 0 1 by n summation n 0 to n minus 1 x square n minus sigma square by lambda. For this MLE p naught cap, we can find out that we decide h1 or h0 if n by 2 g p naught cap lambda by sigma square plus 1 greater than less than log e gamma, and here gx, the gx, it is x minus log ex minus 1. So we can also write as p naught cap greater than less than sigma square by lambda g inverse 2 by n log e gamma minus 1. So we decide h1 if the power p naught greater than this gamma dash, and consider this is the new threshold gamma double dash. So we decide h1 or h0 if summation n 0 to n minus 1 x square n greater than less than gamma double dash. Now consider the weak random signal detection. Consider the previous example 77, and if the random signal Sn is in presence of white Gaussian noise with variance of sigma square, and has the signal covariance matrix Cs is equal to P naught C as in previous case, and P naught is equal to RSS naught, and P naught is known and P naught is unknown and C is known here. So the detection problem is under hypothesis H naught P naught is equal to 0, and under hypothesis H1 P naught greater than 0. If the signal is assumed to be a weak or P naught is very small, then the detection problem reduces to the test of a small departure of P naught from 0. In this case, if the signal is assumed to be weak or P naught small, then the detection problem reduces to the test of a small departure of P naught from 0. In this case, locally most powerful LMP detector can be employed. So we decide H1 or H0 if the test is statistic. This is the differentiation of the log of PDF under hypothesis H1 with respect to P naught. So Tx is equal to del log EP x P naught H1 divided by log EP naught, and where P naught is equal to 0, it will be greater than less than threshold value gamma. And the advantage of this detector is that only a derivative is to be evaluated. So MLE evaluation is not required in this process. And so the PDF under hypothesis H1, it is 1 by 2 pi to the power n by 2 under root determinant of the matrix P naught C plus sigma square I into e to the power minus 1 by 2 x transpose inverse of the matrix P naught C plus sigma square I into x, or I can write it as in log form log e p x P naught H1. It will be n by 2 minus n by 2 log e 2 pi and minus 1 by 2 determinant of P naught C plus sigma square I, and this minus 1 by 2 X transpose P naught C plus sigma square inverse into X. To evaluate the derivative, we use the formula as del log E determinant C theta by del theta. It will be equal to trace of the square matrix C inverse theta del C theta by del theta. So it will be del C inverse theta by del theta is equal to minus C inverse theta del C theta by del theta C inverse theta, and let C P naught will be equal to P naught C plus sigma square I, since since delta C P naught by delta P naught is equal to C. So del log E P X P naught H1 by del P naught, it will be minus 1 by 2 trace of the square matrix inverse of P naught C plus sigma square I into C plus 1 by 2 X transpose inverse of the matrix P naught C plus sigma square I into C and inverse of the matrix P naught C plus sigma square I into X. Here the trace of a square matrix TR, it is TR, a trace of a square matrix. It is the sum of its diagonal elements. Sum of its diagonal elements. So for example, if you have A is equal to 2 1 5 2 3 4 0 1 0, then trace A, it will be 2 plus 3 plus 0 is equal to 5, and the trace of a square matrix have some properties, like the first property is trace A plus B to matrix, so it will be equal to trace of matrix A plus trace of matrix B, and the second property is trace alpha A, it will be trace alpha trace A, and third property of the trace of the square, it will be trace A transpose, it will be equal to trace of matrix A. So now here we can have at P is equal to P naught, the test statistic, it will be minus 1 by 2 sigma square trace C plus 1 by 2 X transpose C X by sigma is to the power 4. So we decide H1 or H0 if the Px, the X transpose Cx greater than less than 2 sigma square gamma plus 1 by 2 sigma square trace of the matrix C. And if I consider it as the new threshold value gamma dash, then X transpose Cx greater than less than gamma dash. So if this value is greater than the threshold value, then we will decide in favor of H1, and if less than threshold value, then we will decide in favor of H0. So far in this lecture, we have discussed about Gaussian random signal with unknown parameters, and also the general Gaussian detection, and also we have discussed the detection of weak random signal. This was 22nd lecture of the lecture series of random processes detection and estimation. In the next lecture, we will discuss about non-parametric detection. Till then, thanks for listening this lecture. Thank you.